what do you need to know to connect your electrical signal to your actual device? What is happening to your electrical signal? What's the next stage we are talking about now? The next stage is from your sensors or your actuators, the transition, analog digital conversion, and then the connection to your actual signal, to your actual device. So this is a bit 101 for the engineers, but I still want to actually put this out there for everybody. Your classical signal chain, if you convert signal from the outside world, is very, very often you have a very small signal to begin with, and this small signal is also full of disturbances of all kinds, of all sorts. Engineers usually use the word noise for that one, and if they're mathematically inclined, they use Gaussian noise for that one, which we'll talk about in a minute as well. Then you amplify that one. Unfortunately, it amplifies your systematic interferences or your noise or whatever you assume that is in the same way. What you have as the next stage is you have usually on the electronic side some basic filters which eliminates what you think is noise. How do you define what is noise and what is signal? How do you know that?
You just have to split it out and get rid of the little bumps.
The little guys are noise, the big guys are not.
Well, yeah.
Yeah.
You kind of have to know what you're looking for.
Yeah.
You have to know the characteristics of the signal so that you can look at things that are outside that.
Yeah. You have to do your homework. You have to know exactly what is the signal supposed to look like. What do you consider the actual possibly useful signal? And it's not the case, as a matter of fact, that you always assume the high frequencies to be the unwanted component of that one. In many situations, what is the classical low frequency which we are always filtering out? Which frequency are you always filtering out of your measurement systems? 50 hertz. Right? Because you cannot do anything, you cannot measure anything without measuring 50 hertz at the same time. Why?
Mains frequency.
Yeah, but why is the mains frequency turning up on my measurement?
What do you choose directly?
Then I use a battery. So I power my little thing with a little battery. I have my thermometer, which is this little device with a battery in it, has no connection to mains whatsoever. I still measure 50 hertz. Why? Yeah. Yeah. We are all living and have been growing up in a world which is humming in 50 hertz all the time. It's very hard to escape this anyway. You really have to actually go mountaineering to get out of 50 hertz hum environments. Here, indoor environments have such a strong 50 hertz hum everywhere. So it's electromagnetically so strong that you will have this on all of your measurements. This is the first thing you usually want to get out. This is a quite low frequency. Right? But it's annoying because you want to measure something very high frequent, which is the opposite here, which is just the tiny wibble on your 50 hertz hum, which just goes quite strong through your whole thing. So you actually flatten out the 50 hertz hum and leave with the high ripples there. Again, you simply have to know what is your signal and what you want to get rid of.
In that case, if you're taking out the 50 hertz,
Yeah.
you end up with your little wave,
Yeah.
at which point, relative to that little wave, you have even littler waves, which are your real noise. In the more classical,
Yes.
just randomness sense.
Yes. Okay. Is there something like Gaussian noise? Do you assume that you measure everything with a bit of Gaussian noise on top of it?
It's mathematically nice, but not always.
Engineers. Where do you get your Gaussian noise from? Everywhere.
It's just like the sum of all the uncertainties.
The sum of all uncertainties. But the sum of okay, it's a bit philosophical.
All the effects that can influence the system and get affected in different ways.
The short answer is it is wishful thinking. There is no such thing as Gaussian noise, but it's the closest thing which we can do easily. So if you assume that you just have a bit of Gaussian noise on that, you have a filter filtering that thing out, and you actually kill a lot of it in the process. But no, you do not kill all random noise of your system in any way. It is just a mathematical abstraction of what you would have there. We are not living on a planet which has Gaussian noise as the major effect in here, because we are not mathematically clean enough for that. All the effects which we have saturation to it. The moment you have saturation to that, there is no Gaussian noise. Gaussian noise assumes that you have full bandwidth signal. Those signals don't exist on our planet. If you remember back the mathematical side of modeling Gaussian noise, you have made a number of assumptions which are actually not true on this planet. Still, they're very handy to do that, but you have to be aware this is an abstraction. So, next stage. Sample and hold. Why do we have circuitry for that? What does that do? Yeah.
Gives you a constant voltage you can measure without changing.
Mm-hmm. Why do you need to actually keep that?
Further down electronics, you get fluctuations in the
Yeah, but I mean, I have a sine wave, a nice sine wave in my signal, right? And then I want to convert this. Why wouldn't you be able to just wire up a converter which says that I want to measure the voltage now?
Take the time for that measurement.
Propagation delays would get added up.
Well, I just subtract the propagation delays and say, well, I will start my process a little bit earlier so that by the time I say now, this will be the right point in time. So it's not about latency, but you are right. Any kind of measurement is not instantaneous. You always have to measure over a minimum time window. Nothing you can measure instantaneous. It always has to accumulate a certain effect over time. It's something you don't mentally take into consideration because you think in terms of clock speeds and look into that one. But even your AD converters, which you have in pretty fast devices, still have a little window in which they're actually looking at the whole thing. And that window is not infinitely small. For that reason, the simple thing you can do is you just hold your signal for a moment, you convert it, and you give your converter enough time to convert that one, and then you can let it go again. That makes it easier for the conversion process. We'll see later on that not all conversion systems will actually use that, because some conversion systems, besides the fact that they're also not instantaneous, but they're also not confused by the fact that the signal is moving. Okay. And next stage is the AD converter. The AD converter, what does an AD converter do?
Basically cycles from 0 to high and tries to match the sample and hold signal to that sweep.
So it has, say, how many 1,000 different comparators, and it just compares, is it larger than that? No. 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 It goes for a while. And at some point it says it's larger than that. Yep. So that's your level. That's an AD converter? We'll talk a lot about AD converters, don't worry. We'll go into a lot of detail about AD converters. So AD converters come in many different fashions and shapes. And if I leave it just for you as a homework now, if I would say that design an AD converter, you probably would come up with lots of different strategies how to do that. The task of an AD converter is you have an analog signal and you want to create a binary representation of that or some digital representation of that in the end so that you have a number representing this analog value. And how you transfer that, there are many different ways of doing that. And again, you need to actually know which one to use because they are radically different in their characteristics. Then you have them in the CPU and you provide them to some latch which does the opposite of your sample and hold to the outside. Then you have a DA converter. The DA converter converts your signal into an analog signal. Why does it look so bad? That looks pretty glitchy, right? Why does it look so glitchy? Well, what do you ask of this DA converter? What is the input for the DA converter?
You're asking for an instantaneous voltage change?
Yes. This is the same argument as for the sample and hold. You are asking at the DA converter for an instantaneous voltage change. And if you ask an analog piece of circuitry, an amplifier, for an instantaneous voltage change, what will your amplifier do? Right? It will not be able to do it because that would need to have infinite bandwidth in or infinite available frequencies here. No device can possibly do that. You're always bandwidth limited, which means you have the choice of either going or you overshoot. And usually you have an educated mix of that so that you have a reasonably fast response and you have a little bit of glitching still in the system there. So it means after the raw DA conversion, you need to have a deglitching stage, which is basically a low pass. So that beyond a certain point, it's a bit unrealistic, and you make this thing a bit. This is a low pass for very high frequencies, which are targeting particularly these glitching frequencies, and then you run it through an actual low pass usually to smooth it down to the original signal. Lots of conversion stages which are happening there, and a lot of them are electronics. Who in the room has actually had an electronics course? Has had, yeah, okay. And you would be able to define and design instrumentation amplifiers, operation amplifier circuitry. I have one nodding, two nodding. You're supposed to do, but you forgot about it. You would be able to do it? You could try. Okay. The computer science crew has no idea what we're talking about. So we need to understand a little bit what the electronics behind that can actually do. But don't worry, we are not making electronics course out of the whole thing. But where the knowledge ends for the engineers is usually when it comes to AD converters. You may have seen a single form of AD converter, but that's probably the extent of your knowledge, and you need to know a lot more about AD converters before you can use that in the real world. Okay. So, right. Sampling. You're all familiar with Nyquist's theorem. Again, I have a weird nodding which is very close to the front here, and not much else here. Okay, what does that do? If you sample your data with a certain frequency, the measurements which you get is that. So assume all of that would work, what we saw in the slide before, and your computer or your microcontroller sees those values at those times. What do you assume about your signal? What does your actual signal look like now? No idea? You can't tell from that. How about that? Would you assume your signal looks like that? Could have a bit of noise on top of it. Yeah. But if the noise would be always hitting exactly those measurement points, you would probably just ignore it anyway. Of course, you always can have a bit more noise on top of the whole thing, which you probably wanted to get rid of if you sample that slow anyway. If you sample that slow, you didn't want to measure that in the first place. But unfortunately, there's a much worse effect. What is the much worse effect? The much worse effect is this one. I'm sampling with a higher frequency now, and I'm getting my red signals. Now the point is that the same signal? Can you tell? So maybe my signal was actually this one. And you see that those blue measurements would have exactly measured the same thing as would have at the red measurements at a higher frequency. And that is called aliasing. The effect that the signal looks actually quite different from what you assume it looks like based on the low frequency which you measured there. And not just in terms of noise, but systematically different. This is a very different signal than the other one. It's not just the other one with a little bit of noise on it. What's the solution for that? How do we get out of that one? Because now I can just play that game continuously and say that, and now I measure a little bit more frequently again, and that will trick you again into, well, actually, the real signal is something completely different. Right? But that's not comfortable for you now, because you're measuring something at a certain frequency, and you want to be sure that this makes sense, and I can actually interpolate the measurements which I get in a sensible way without running the risk of assuming that possibly my signal looks completely different. And fortunately, this is what you get from the Nyquist criteria, which is probably one of the most important theorems out of information theory, that in order to correctly measure a signal, you have to sample this with at least double the maximum frequency of the sample signal. You have to always sample with at least double the frequency of what you want to measure. How do you guarantee that?
You have to have knowledge about what you're going to be measuring before you start.
Yeah. And if you're a little unsure about it, you just kill all the higher frequencies before you do that. You just have an electronical low-pass filter in front of that, and you say that, well, I make sure that there is no physical way how any higher frequency could actually get to my system to start with. Or you already know that the highest frequency in my signal which I want to measure is only this, so my sampling is fine. Okay, that's great. Perfect measurements taken at that frequency will result in no information loss. So you have full information of your incoming signal. Now this is great. That is a very strong guarantee. Is it true? Can you go to your boss and say, I sampled this signal at that frequency, I have not lost anything. This is 100% of the original signal, which I measure here, which I can reconstruct now.
That would be great for custom signals where you have overlapping or complex changing things or like audio file.
No.
Doesn't help.
No. This is holding true for any signal, regardless how shaped. This is not, I mean, for cartoonish reasons, this is a single frequency signal here, but you can have any kind of complex shaped signal here, as long as the highest frequency is only half or less than the maximum sampling frequency, than the sampling frequency. Then Nyquist tells you that you get the full information back. Do you buy into it?
It does take perfect measurements.
Exactly. You're the only guy who read the fine print. This is only true if your measurement is perfect. What does that mean? What does it mean for your AD converter, for example? If you have an infinite number of bits available to measure this signal, right? Now your AD converters are, say, 10 bits, 12 bits, 14 bits maybe. Now 14 bits is great, but it's a fair stretch from perfect. Right? So you have to be a little careful about that because your measurements are not perfect. And as your measurements are not perfect, you're usually doing that. Oversampling, which is always confusing if you do this in a first year lecture. You just introduce this is perfect information reconstruction, and now we have perfect information reconstruction, and we sample a bit more. Right? This is exactly what you do. You sample a bit more because with a little bit more realistic knowledge about how to convert signals, you know that your conversion is not perfect, and you need to sample a little more frequent than that. So you do, in fact, use oversampling, which means you're sampling at a higher frequency, quite significantly often, than the double frequency, twice the frequency of your maximum frequency in your incoming signal. Okay. And this is mostly due to the quantization effects which you have in your conversion stages. Does that make sense to everybody? Yeah. Okay. This is how that looks like. Why is nobody stopping me? This is how this looks like in it's the last slide, don't worry. The quantization effects. This is your analog input. This is your ideal digital output. Cannot get any better than that. Perfect, wonderful, spot on. And here we have a number of terms defined. And inside each of these errors here, we have completely unavoidable a certain amount of error range with every measurement you do. And this error range is expressed as the quantization noise, which is depending on the number of bits. So you can either express this as this is 1 over 2 to the power of n, which is probably how a computer scientist would look at it. Or as an engineer, you look at it in terms of decibel, and then it's n times roughly 6 decibel, which you have as your quantization noise in your system. Okay, and this is the ideal case, which means your mean square error is already this. you look a little bit too out of your comfort zone by now. I think we should actually do this in the next session a bit more seriously and in more detail. But one outlook I want to foreshadow already, and that is if you look at this graph here, you can imagine that there is no AD converter on this planet which actually looks like this. Your AD converters will actually have very different characteristic curves in their data sheets, and we have to understand what are the parameters here which you get from your AD converter manufacturers to understand what is actually happening here. Just as foreshadowing, you will, for example, assume at the moment that you will use every little bit, every little step in your AD converters physically, and on the data sheet you have a field which is very confusing, missing bits. How on earth would somebody sell you an AD converter where bits are missing? This is like you buy a car where some screws are missing. But for AD converters, it's actually quite common. So that those specific stages will actually not occur. The converters will not produce them. This is normal. So you have lots of non-linearities in your AD converters, which we need to learn about to understand what AD converters you select and how do you read the data sheets in these AD converters. Fortunately, there are a few very powerful characteristics which you should look at in the end. Okay, sorry for running a bit over time. See you. Thanks.